Okay, so we're going to get into chapter 3. And this is all about descriptive statistics. Or we often call it just numeric summaries. Okay? And so what we're doing, and here we're dealing with numeric data. So we're going to have numeric summaries for numeric data. But we can have numeric summaries for categorical data as well. But in chapter 3, we're focusing on numeric data. Okay? So again, think of your data set, all of those rows and all of those columns. And all we're doing is we're just picking one of those columns, okay? We're picking one of those columns in our data set. And so, if your data set has 500 people in it, you've got 500 rows, right? And then we're going to just, maybe your data set has 20 columns, but we're just picking one column, okay? So we're just picking one column in our data set, in our table, and it's a numeric column. So basically, you just have 500 different numbers in there, okay? It could be age, and you've got the ages of 500 different people. It could be, the income level, and we've got the incomes of 500 different people. Or what is your shoe size, or what is your height, or whatever it might be, okay? Just think of, one numeric column, and, it's for your entire data set, whether that's 500 people, or maybe just 50 people, or maybe 5,000 people, whatever it is, okay? And we want to be able to summarize all of that information. So if you got 500 people in there, you don't want to have to list off all 500 people in there, okay? We want to be able to summarize that somehow. And this is what a numeric summary does. It takes all of this number, maybe 500 numbers, maybe 5,000, maybe just 5 numbers, and it just summarizes it down to one number, or a few different numbers depending on which numeric summaries you use, okay? So this idea of taking a bunch of numbers and shrinking it down to just one number is very familiar to you guys already. Maybe you just don't realize it. So you're probably very familiar with this concept of a GPA, okay? A GPA is your grade point average, and unless you just started school in the US, you've probably taken many classes, okay? And at the end of your class, you get a grade, and that grade's supposed to summarize your work in that class. And then you've done this for many different classes, and your GPA is supposed to summarize your performance in all of these different classes, okay? And whatever, so maybe you've taken 30 different classes. The GPA is just one number that kind of gives you an overall picture of how you've done in your entire academic career, okay? And so you lose some detail, but it is useful if you're trying to compare one student to another, okay? If you had to pick out study groups or something, or if you had to pick someone who you wanted to tutor you, I think a relevant question is, what grade did you get in your math, or what's your overall GPA? And you'd probably want to get tutored by someone with a GPA that's at least as good as yours or higher, rather than being tutored by someone with a much lower GPA than your own, okay? So, that may or may not be the best policy. You might have someone who's brilliant in one subject but does poorly in other things, and so the GPA is not going to capture that. But overall, if you just had to kind of make quick comparisons between students or between people, and rather than saying, give me your entire transcript so I can see how you've done in every single class, you can just, it's not really, I guess, socially acceptable to do this, but you can just say, hey, what's your GPA? What's your GPA? Oh, yours is higher. I'd rather study with you, okay? I mean, that people would probably look at you and say, like, you're not a nice person to do this. But companies do stuff like this all the time, right? You have a credit score, okay? And this credit score is supposed to summarize how likely you are to pay back money you borrow, or how on the other end, how likely you are to not pay back the money you borrow, okay? And whether it's a fair system or not, this is a single number that's supposed to represent your credit worthiness, and it's used to make decisions. Do you get this loan or not? And so we have these things, you can think of them as numeric summaries that we carry around with us, whether we like it or not, that companies or different groups or people use to make decisions about us. And in statistics, we kind of do the same thing. We just take a bunch of numbers, a bunch of different things, a bunch of data points, whether that's data points from your own life or data points in a sample of data that you have, and we're just boiling it down to one number, okay? And so depending on the situation, we have custom numeric summaries like GPA, like your credit score. If you want to talk about an entire nation's economy, you can summarize it with a number like GDP per capita or something like that, okay? And that kind of summarizes the strength of an entire nation in terms of economy. Or, for sports, we have, batting average or on-base percentage for baseball, or passer rating if we're talking about football. We've often created custom numeric summaries. We don't call, people don't go around talking about numeric summaries, but, we often have custom numbers to kind of summarize a much bigger thing of information, okay? So, and in our class, we'll just talk about some certain numeric summaries. So let me just kind of summarize what I've just said. Okay, so numeric summaries are numbers that summarize a set of data. Okay, so we take lots of data and boil it down to just a few numbers, or even one. Okay, so examples. Okay, an entire academic career gets boiled down to GPA, okay, or the entire history of one's borrowing record. Okay, or a nation's entire economy. Okay, and we might argue whether or not these are good or bad ways to summarize something, but we do this, okay? Whether it's a good thing or a bad thing, okay? And so these are kind of like custom. These are, quote, custom numeric summaries. Okay, and in our class, we're going to talk about basically two groups of numeric summaries that can be applied to any situation where we have numeric data. Okay, so we have numeric summaries. That can be used in any situation with numeric data. So, and we can kind of classify these into two groups. We have numeric summaries to describe the center of a data set, and these would be the mean and median. Okay, and we have numeric summaries to describe the spread in a data set. And this would be the range, IQR, and standard deviation. Okay, so I'll let you guys get caught up if you're writing. And so we'll talk about each of these numeric summaries, okay? But again, don't lose sight of the big picture, which is these are just ways for us to take a lot of data, a lot of information, and boil it down to just one or maybe a few of these numbers, okay? And the reason why we want to boil it down to just one or a few numbers is so we can kind of make quick comparisons from data set to data set. Okay, so maybe we have one, a sample of data that represents one group of people. We have another set of data that represents another group of people. We have another sample of data that represents another group of people. Okay, we want to be able to make quick comparisons between these groups. Okay, and rather than having to look at every single person individually, we can just look at these numeric summaries. All right, so in the same way, rather than having to look at someone's entire transcript of scores or class grades, we can just say, hey, what's your GPA? What's your GPA? And use these single numbers to make comparisons. Okay. All right, so in our book, the book talks about it says, for data sets that are symmetric, okay, and what does it mean to be symmetric again? Okay, it means whatever's happening up on your high end is also happening at your low end. So if you've got values that exist way up here, you're also going to have values that exist way down here. Okay, that's kind of what it means to be symmetric. And so it says for data sets that are symmetric, okay, we may prefer to use the mean to summarize center, and the standard deviation to summarize spread. Okay, and then it says for data sets that are skewed, okay, we may prefer to use the median to summarize center, and use the range in IQR to summarize spread. Okay, but the truth is all of these numeric summaries can be calculated for any numeric data set, whether it is symmetric or skewed, okay? Okay, but also remember data set. Okay. All right, so let's we'll delve into the mean and the standard deviation first, and then we'll talk about the median, the range, and the IQR, and all of this. Okay. And again, these are being used for numeric data. Okay, so don't, I think on the quiz, I showed you that table, and it was meant to be an easy question. Was the table, with the states and the genders being represented, that was categorical data, okay? So you gotta keep in mind what data is numeric and what data is categorical. Okay, so we're dealing with numeric data, and so the mean, this is a measure of center. And we can think of it as the balance point in our data. All right. So let's say I've got, let's say there is a family with 4 kids. Okay, and the average, and the 4 kids' ages are 10, 11, 13, and 14 years old. Okay, what is the mean age? Okay, well, I think we're familiar with this concept of mean. Okay, the symbol that we use for mean is x bar. Okay, and we get the mean by adding up our numbers. I'll say add up the values and then divide by how many you have. Okay, we're familiar with this concept already, right? And so symbolically we say x bar is equal, add up the values is written as sum of x. Okay, that means add up. And then we put this over, we make a fraction, which basically means divide by n, okay? And n means sample size, or how many numbers you have. Okay, so in our example family, we have we're going to do 10 plus 11 plus 13 plus 14. And if we do this, we get 48. And then we do 48 divided by 4. And we get 12. So the x bar, our average age, is 12. Is that all right? Okay. And then this concept of the balance point of our data, we can think of drawing a number line. Okay. And let's say I made a dot plot, okay? Except imagine these dot plots, the dots are like stones, okay? So imagine I've got this board, and I've got these stones at 10, 11, 13, and 14. And if I wanted this thing to be balanced, where would I put the little, the seesaw triangle, the fulcrum? It would go right here at 12, and this thing would then be balanced, right? This is our balance point, and so our balance point, x bar, is equal to 12. All right, and so when the let's say we had another family, except the ages of the kids, they're quite similar, is 10, 11, and 13, except the oldest kid isn't 14, the oldest kid is 20, okay? So, so we'll say, can I go to the next slide here? Okay. So, this was the other family where the kids are 10, 11, 12, and 13. Don't draw these same dots. I gotta get rid of this this one, 14, and we're gonna move this. So 16, 17, 18, 19, 20. Okay. So this is now at 20, and so our oldest kid is at 20. So we got 10, 11, 13, and 20. What is the mean age now? Okay, well, I would do 10 plus 11 plus 13 plus 20, and I get 54. So the sum of x is 54. This is 10 plus 11 plus 13 plus 20, and then I do 54 divided by 4, and I get 13.5. So x bar, 54 over 4, 13.5. And so if this were my picture, the place where I would draw the balancing point is now over here. Okay. Okay, and so we say that the mean is affected by extreme points. All right, and so, if in this case, this data with the 10, 11, 13, and 20, this is skewed right? Because, if we think of where kind of the middle is, it's somewhere over here, and we have one extreme point that's way higher than everybody else. Okay, and because it's way higher than everybody else, that makes it skewed right. So, so our data here shows up as skewed right, and we say the mean is affected by extreme points. And this is why the book says for skewed data, we might prefer to use the median, which is not affected by extreme points. And we'll talk about the median in a little bit here. Okay, so the mean is affected by extreme points. So for skewed data, the mean may not be preferable. Okay, but if you want to use the mean for skewed data, it's not wrong. It's just you got to keep in mind. Okay, so for example, a silly example is maybe in a small town, maybe you're sitting in a diner with with 6 people in there. Okay, and maybe all of these people work at the local factory and make $65,000 per year. So you got 6 people in the diner. What the average income of these 6 people, because they all make the same amount, would be $65,000 per year. Okay, no surprise there. Let's say Bill Gates walks into the diner. Okay, I don't know how much Bill Gates, but let's just makes per year. But let's say he makes 10 million a year. Okay, I have no idea. I'm making that up. All right. So if we ask what is the average income of people in that diner, it would now be 10 million plus whatever pocket change these people make per year, and then the average income would now be something like $1.6 million per person. if we look at the people in the diner. And that would not be an accurate picture, or maybe it is. I don't know. The mean might not capture the essence of what we might think of as the typical or the central value that shows up. And so the mean is affected by those extreme points, which may or may not be suitable for your application. Okay, in the insurance business, they're constantly worried about the mean. Okay, so your typical person who drives a car, if you got car insurance, your typical person will cost the insurance $0 in payouts. Okay, because most people will get through the year with 0 accidents, and so the insurance has to pay out $0. Okay, but would it be a smart idea for the insurance to say, oh, well, our average payout is 0, so we can charge tiny premiums. We can just give coverage at $10 a month or something. That would not be smart, because every now and then you got someone who gets in an accident and it costs the insurance company $100,000 or something like that to make all the repairs and pay for medical bills and whatever. And so because of that, everybody else, or the whole company, whoever's paying the company, has to pay probably a couple $100 or more in premiums per month. And it's because they're worried about those extreme values to balance things out. So maybe you want the extreme values, maybe you don't. Okay, it all depends on context, the situation you're dealing with. Okay, so that's the mean, and we use X bar to symbolize the mean. Okay. There's this other concept, and this is spread in our values. Okay, and so we could have 2 families. I could say there's 2 families. Both families have 4 kids. And the average age of the kids is 12 years old for both families. Okay. And you might think, oh, well then these 2 families are similar. But I'm going to write down the ages of those kids, and I hope you'll realize these families are actually quite different, because I've left out a critical piece in the story, and that is the spread in ages. So we'll say, we got the Jones family, and the kids are 10, 11, 13, and 14. Okay? Average age, X bar here, is 12. Okay? But let's look at the Smith family, and the ages will be 4, 8, oh no, sorry, I gotta change this. It'll be 6, 10, 15, no, 6, 10, 14, and 18, okay? The average age here is also 12, okay? But life at the Jones family probably looks quite different from life in the Smith family, right? Okay? So, these families, these are both very plausible families of 4 kids, okay? But, the life in each family probably looks quite different, okay? So, and that's because the spread in ages in the Smith family is much greater than the spread of ages in the Jones family. Okay, so this concept of spread, okay, Okay, and so so we have a numeric summary to capture this idea of spread. Okay, so so I mean, right now, because of the example is so so simple, it's easy to say this has high spread and this has low spread. Okay, but you can imagine for a larger data set, we don't want these just loose terms of large spread and low spread, and it might be useful to have an actual number that says this is the amount of spread that we have and this is the amount of spread that we have. Okay, and so the number that we use to capture this idea of spread is known as the standard deviation. So the standard deviation, okay, is a numeric summary for spread. Okay, and it captures the idea of, are, you know, the ages, or are the values quite spread out, or are they all quite close to each other? Okay, so you know, the Smith family, I don't know, that maybe they were very methodical in their planning of children or whatever, and you know, they spaced them out 4 years each out at, you know, 4 years apart, and so you know what happens is, you know, the oldest kid is getting ready to go to college while the youngest is just entering first grade. So you got this wide range of spread in ages. Okay, whereas you know, in the Jones family, they, you know, one kid right after the other, maybe a small break in the middle, but you know, it's probably, you can imagine as they're going through elementary school, you know, each teacher's like, oh, did I just have your brother in class? Or, you know, was your sister in the class of the year before? Something like that. See, you can imagine something like that. In both families, they have 4 kids, and the average age is 12, but the picture of what's going on is quite different. And so the difference between these two families is that the spread is much bigger over here than it is over here. Okay, and the standard deviation is just a number that captures that idea of spread. Okay, so standard deviation is a term we're going to see a lot in statistics, but don't lose sight of the big picture, which is just, it's a numeric summary. It's just a single number that captures this idea of spread. Okay, and we'll go into the calculations, but that's the important part. Did I see a hand raised with a question? No, we're okay. Yes?
Are we still going to be calculating the spread even when the, what is this we have?
Standard deviation, or?
The 12, what is it?
X bar?
Yeah, the X bar.
The mean?
Yeah, the mean. If the mean is different, are we still going to be calculating that spread?
Yeah. I mean, it's just a numeric summary. It's just, you know, this was an illustration to say it's not enough to say there's 4 kids and the mean is this. Okay, it's not enough to say these 2 data sets have the same average and the same number of data points. Okay, so yeah, you could have different, you know, different means, and that's fine. We're just saying this is one thing that we want to capture, this idea of spread. Okay, so standard deviation is a numeric summary for spread. Okay, it's just it's a number that captures how much spread we have in our numbers. Let me I'm going to copy these numbers over onto the next slide. Okay, so let's talk about calculating the standard deviation. Okay. Okay, so standard deviation, the symbol is S. Okay, the standard deviation is S, and you can think of as S, the standard deviation is the square root of the variance. Okay. Okay, and the variance can be thought of as the quote-unquote average, and I have average in quotes here, and you'll see in a moment here, squared distance from the mean. Okay, and so So let's look at the Jones family, okay? So the Jones family, the ages are 10, 11, 13, and 14, okay? So, you know, our first step is find the mean, okay, which we've already done, and we have x bar is equal to 12, right? But if I didn't give you that, it would be easy. You'd add them up and divide by 4, and you'd get the mean, right? Okay, so now we're going to find the distances from the mean. Find the distances from the mean. Okay, so I'm going to do that on the next line here. So we say, how far is 10 from the mean of 12? How far is 10 from 12? It's 2 away, right? So the distance is 2. How far is 11 from 12? 1 away. How far is 13 from 12? 1. And how far is 14 from 12? 2. Okay, so these are the distances from the mean. Essentially, all I did was just I subtracted the mean from each value, right? Okay, and we could put in the negatives if we can leave them off. It doesn't matter, okay? The next step will then be to square these distances, because the variance is the average square distance from the mean. So we're going to take these distances and we're going to square them. Okay, so what is 2 squared? 4, right? 2 times 2 times itself is 4. 1 squared is 1, 1 squared is 1, and 2 squared is 4. Okay, so is this row of red numbers okay with everybody? All we're doing is we're just taking the distances from the mean and we're squaring them. Okay, and then so steps 4 and 5 would be find the average, right? Quote, average these square distances, which we do by add them up, and then normally to get the average you would add them up and divide by how many you have, right? You would divide by n. But I have average in quotes, which is divide by the quantity n minus 1, okay? And this is a funny thing known as Bessel's correction. You don't have to worry about the math behind it. There's a good reason why we use n minus 1, but all you have to worry about is that we do this, okay? So we're going to add these numbers up, excuse me, and divide. Instead of 4, we're going to divide by 3, okay? So what do I end up getting? I would get 4 plus 1 plus 1 plus 4 equals 10, and then I would do 10 divided by 3, and I get 3.333. Okay? And so this number, 3.333, this is the variance. Okay, so the variance is our, quote, average squared distance from the mean. And this is our variance. And so the last step to get the standard deviation is take the square root of the variance. Which is what we get in step 5. So the square root of 3.333 is equal, oops, 1.826. Okay, and so my standard deviation of the Jones family kids ages, S is 1.826. Is that good with everybody? Yes?
Will you explain one more time how you got 10 divided by 3?
Yeah, so I added up 4 plus 1 plus 1 plus 4. So I added up the numbers in red to get 10. Okay? And then, so that's step 4, add them up. And then I'm dividing, instead of, I'm dividing by n minus 1. So instead of dividing by 4, because normally if I said take the average of these numbers, you would add these 4 numbers up and divide by 4. Okay? but we do this funny thing called Bessel's correction, which is we add them up, but we divide by 3 rather than 4, okay? And the math is complicated behind it. So, you know, I mean, you can go on Wikipedia and look up Bessel's correction, but it's probably more math than you want to deal with. Just know that that's what we do. Yes, question?
So with Bessel's correction, if we did have 5 numbers, we would divide by 4.
Yes, yes. If you had 5 numbers, you would divide by 4. If you had 300 numbers, you would divide by 299, okay? So it's just 1 less than however many numbers you have, okay? And that's getting the standard deviation, okay? All right, so I'm going to race through calculating the standard deviation for the Smith family. I'm just going to run through these same exact steps, and we will get the standard deviation for the Smith family, okay? So the average here is 12, so, you know, I'm going to do 6, 10, 14, and 18, and then I subtract 12, and so I get 6, this is 2 away, 2 away, and this is 6 away, 36. I'm squaring these, right? And then, oops, this isn't 4, this is 36, okay? And then we add them up, so 36 plus 4 plus 4 plus 36, and this gives me 80. And then I do 80 divided by 3. And so I get 26.667. This is my variance. And so my standard deviation is the square root of that. And I get 5.1639. Okay, so over here, my standard deviation of these ages is 5.164. Okay, so I know I did that quickly, and you know, if you couldn't keep up, that's okay. But basically, I just ran through the same exact steps that I did on the previous page. Okay, all to say, looking at these 4 kids and their ages, the mean is the same, but the spread is different. The standard deviation is 5 over here, the standard deviation is 1.8 over here, and that captures this idea that the ages are more spread out in the Smith family than they are in the Jones family, okay? So the standard deviation is a way for us to capture this idea of spread, okay? So the standard deviation shows us that the ages in the Smith family are more spread out than they are in the Jones family. Okay? And we already knew this looking at the ages themselves, but you can imagine any other data set where you've got lots of data points and it may not be clear. You can throw them into a formula like the standard deviation and or throw it into the process of the standard deviation and get it out. Now, some of you ask for formulas. I'm going to draw this, okay? But if you don't like it, don't worry about it, okay? Okay, this sums up all of the steps that we have, okay? So step 1 was find the mean, right? Step 2 was take the difference of each of these, subtract the mean from each value, and then we're going to square those distances, so that's the square that you see there. The 4th step was add them up, and then the 5th step was divide by n minus 1, and the 6th step was take the square root, okay? So all 6 steps that I listed out on the previous page show up in our formula for the standard deviation. Now, some of you guys can look at a formula like this and say, oh yeah, I see all 6 steps. Others of you, you look at formulas and as soon as there's more than 3 letters in there, it gets confusing and you're just like, don't worry about it. Don't worry about it then, okay? If you can say, hey, I don't like formulas, but I can follow these 6 steps listed out on this piece of paper, then stick with that, okay? Do something, whatever you're comfortable with. There's no sense in trying to make the subject any more difficult than it needs to be, okay? Just what works for you works for you, so that's fine, okay? If you like formulas, here it is, and it shows all of this, but don't worry about it. Okay, we still have a more to cover, okay? We have this concept of z-scores, okay? Now z-scores, these combine the mean and the standard deviation into a concept of, this tells us how extreme a point is, okay? All right, and the definition of a z-score, the z-score is equal to our distance from the mean measured in standard deviations. Okay? All right, so imagine you go to the doctor, okay, and you get some blood work done. They say, oh, and let's just, for the sake of this illustration, we're going to just make up something. So let's say, they draw blood and they say, you know what, I want to get your XYZ levels tested, okay? So they run it and they say, okay, we got your XYZ results back. And they say, your XYZ score is 253. And you say, well, I have no idea what an XYZ score is, okay? So is that high? Is that low? They say, your score is 253, and the average score is 150. So, and then you're like, well, okay, I'm above average, but still, you don't know if 253 is way higher than average, or maybe it's not that much higher. So if the doctor says, well, normal is considered 120 to 180, then you'd be like, oh dear, my XYZ is really high, okay? On the other hand, if the doctor says, oh, well, normal is anywhere from 0 to 300, then you'd be like, oh, well, 253, that's on the higher end, but I'm still in the range of normal. You can breathe a sigh of relief, right? So in both of those things, what matters is where the center is, where the mean is, and also the spread. The range of normal, is it from 120 to 180? Is the spread this? Or is the spread from 0 to 300? Is it much bigger? Okay? And the z-score uses both the mean and the standard deviation, our distance from the mean measured in standard deviations. And this will give us an idea of whether something's extreme. And so instead, the doctor could say, oh, your z-score is +1, okay? And that means you are 1 standard deviation above the mean, which means you're on the high end, but usually not something to worry about. But if they said your z-score is +3, that means you are 3 standard deviations above the mean, and I'll show you in a moment that being 3 standard deviations above the mean is something that's very unusual, okay? So the formula for a z-score is basically our distance from the mean. So we just take our value x and we subtract off the mean, x bar. So this is our distance from the mean, but we measure it in standard deviation. So we're going to take that distance and we're going to divide by s. Okay? So the numerator is the distance from the mean. and then and we divide by S, the standard deviation. Okay? And so I hope that gives you a sense that, oh yeah, this is the distance from the mean measured in standard deviations. This is not that big of a deal. It's just like saying, how far is that door from me? That door, I could say, is 120 inches away from me. Okay? And in your head, you'd say, oh, 120 inches, that's 10 feet. Okay? So all you're doing is you're just taking the distance that I've reported, but you're converting it in your head by dividing it by the size of 1 foot, and you're going to say 120 inches divided by 12 is 10 feet. Okay? And that's all we're doing. We're just taking the distance. So from here to that door, maybe it's 120 inches. I'm just making that up. Okay? You're just taking that distance, and then you're dividing it by the size of your standard deviation. Okay? And this goes hand in hand with what we call the empirical rule, which states that about 2/3 or about 68% of the data will be within 1 standard deviation of the mean. About 95% of the data will be within 2 standard deviations of the mean, and then about 99.7, so almost everyone of the data three standard deviations of the mean. Okay? And so that means, you know, to be 3 standard deviations or more away from the mean, whether it's 3 standard deviations above the mean or 3 standard deviations below the mean, to be that far extreme from the mean is very, very unusual. 99.7, so that's almost 100%. The vast majority is within 3 standard deviations. Anything that's more has a standard deviation or a z-score of more than 3, okay? So, you know, z-scores over 2 or, you know, less than -2 are unusual. And then z-scores over 3 or less than -3 are very unusual. Okay? And so we can talk about how z-scores also allow us to compare apples to oranges. Okay? So we said, you know, in this example with the doctor, you can get your blood work tested. And rather than the doctor saying, oh, okay, the average is 150 and the range of normal is from here to here, the doctor can say, oh, your z-score is plus 1.2. So you say, okay, that's on the high end, but it's not that unusual, okay? But if the doctor says your z-score is plus 2.8, you'd say, oh, that's quite unusual. And if the doctor says it's plus 3.4, you'd say, oh, that's very unusual, okay? Or if the doctor says your z-score is negative 3.4, then that's very unusual, but in the lower end, okay? So, you know, these are good guidelines. Z-scores over or under 2, -2 are unusual, and z-scores over 3 or less than -3 are very unusual. But also, you know, maybe your XYZ score is fine, but maybe your JKL score is extreme or something like that, okay? And so you can start comparing things and say, oh, is this thing weird or is this thing weird? And so, you know, maybe we have an intuitive sense of things, but we could say, you know, what's more unusual? A man who is 6'5" or a woman who is 6'2", okay? And you know, if you're not, you know, if you're unfamiliar with human heights, you would not be able to answer this. But what we can do is we can convert these heights and say, oh, the man who's 6'5", that's unusual. His z-score is plus 2.5 or something like that, okay? But then we say, oh, the woman who is 6'2", her z-score is actually plus 3.1, okay? And so these are both very tall people, but compared to other women, this woman who's 6'2" and having a z-score of plus 3.2, and I'm just making these numbers up, is more unusual than the man who is 6'5", who has a z-score of plus 2.5 or something like that, okay? Is that concept okay? And so, you know, we can use z-scores to decide what is more unusual. Okay, and we'll say, you know, basically, the farther a z-score is from 0, the more unusual it is. Okay, so, you know, let's just try an example. Let's do, man is 6'5", which corresponds to 77 inches tall, I think. Okay, and we will say the mean height of men is 70 inches and the standard deviation is 3 inches. Okay, and so this man's z-score would be 77 minus the mean of 70 divided by the standard deviation of 3. Is that okay? And so we do 77 minus 70, and I divide that by 3. So this man's z-score is 2.33. So a man who is 6'5" has a z-score of 2.33. Is that okay? These calculations? All right, and then let's talk about the woman who is 6'2", okay? So we'll say the mean height of all women is 5'4", so that's 64 inches. And we'll say the standard deviation of all women is also 3 inches, okay? So 6'2", this would be 74 inches, right? Each foot is 12, so 12 times 6 is 72, plus 2, 74 inches. And so this woman's z-score would be what? I would do 74 minus 64 divided by 3. Okay, so I would have 10 divided by 3. 74 minus 64 divided by 3, I get 3.333. 3.33. Okay? So a woman who is 6'2" has a z-score of 3.33. And so indeed, we would say the woman who's 6'2" is more unusual than the man who is 6'5". They are both considered unusual, right? So anything with a z-score of more than 2 or less than -2 might be considered unusual, but anything with a z-score of 3, more than 3 or less than 3 would be considered highly unusual. Okay, and I think, you know, I kind of made up these mean and standard deviation numbers, but they're fairly close to reality, and I think this matches our intuitive sense, right? That a man who is 6'5", we would all consider him tall, but not extraordinarily tall. A woman who is 6'2", we would say she's very tall and quite remarkably tall. I would think we would say something like that. Okay? So, so we have that going on. All right, so that covers means and standard deviations and z-scores. I got 20 minutes left, and I'm going to cover the other topics, the median, the IQR, and the range, okay? And I think I can do it, all right? So we just got to stay focused here, okay? So going back, the median is a measure of center, okay, is a numeric, I should say, is a numeric summary for center. The mean, we said, can be thought of as what? The balance point of our data. The median can be described as the middle or the center point. I'm sorry, can be thought of as the halfway point in our data, okay? So the median is the halfway point of our data. Okay, so the mean is the balance point of our data. The median is the halfway point of our data. And what we mean by that is that half of the values in our data set are smaller than the mean, smaller than the median, and half of the values in our data set are larger than the median. Okay, half of the values in our data set. Okay, so I think that's a simple enough concept. And so to find the median, what we do is we count how many data points we have, we arrange them from least to greatest, and then we say, okay, if I've got 30 data points, I need to find where the spot where 15 are smaller and 15 are bigger. If I've got 500 data points, I need to find the spot where 25 are smaller and 25 are bigger, okay? And then if you have something like 11 data points, you've got an odd number, so you do 11 divided by 2, that's 5.5. Basically, you're going to say, okay, 5 are going to be smaller, 5 are going to be bigger, and then the one in the middle, that's my median. Okay, so to find the median, okay, count how many data points you have. Okay, arrange your data from least to greatest. Okay, and find the spot that divides your data into two groups. Okay, so, you know, with 20 data points, or 10 are less, and 10 are more, or are greater. Okay, and then with, so I'll say with 21 data points, then what you will have will be 10 less. You're going to have 10 more, or 10 greater, and then you got one value here, one value in the middle, and this value is the median. Okay, with 20 data points, you got 10 less and 10 are greater, okay? And then you would basically take the value in between those two middle points will be your median, okay? So, you know, maybe I'll just do a quick demo here. Or, I don't know, I'll write this value in between the two middle points is the median, okay? I think many of us are already familiar with the median, okay? And maybe in elementary school or junior high you were taught, like, list them out and then like start at the ends and then count towards the middle. That's an inefficient way, but if you do that and you're careful, it will also get you to the median. I think this way of just kind of counting where half are greater and half are less is much faster, okay? So before we do an example, I want to talk about these next few things. So the median is a numeric summary for center. And then we also have two more summaries, numeric summaries for spread, okay? So we already have one numeric summary for spread. And what is that we've covered? Standard deviation, that's the numeric summary that we've already covered for spread. We got two other numeric summaries for spread, and these are the IQ, well, I guess first I'll do the range and the IQR, okay? And the IQR stands for interquartile range. Okay? All right, so the range is just the largest point, largest value minus the smallest value. And this is kind of like how far apart are your extreme values? Okay, so you can say, you know, in my classroom, the oldest student I have is 80 years old, and the youngest student I have is 18. And so I have a range of 80 minus 18, 62 years, or whatever like that. Okay, and so you say, but maybe the range is not that big. Okay, or maybe it's an unusual thing to have students, you know, or someone who's at the extreme points, and so maybe it's better to use the interquartile range, okay? And what the interquartile range is, this is how far apart are the ends of the middle 50%. So you think of the middle range, okay? So you think of dividing your data into kind of 4 chunks. You know, how far are the two middle chunks, the extreme ends of the two middle chunks are, okay? So this is how far apart are the extreme values, are the, quote, maybe I'll say end values of the middle 50% of the data. Okay, and formally we define this as Q3 minus Q1, or third quartile minus first quartile. All right, and that's why it's called the interquartile range. All right, so maybe I have to define what Q3 and Q1, what are quartiles, okay? So Q3 is the third quartile, and what this is this is the spot in our data where 3/4 or 3/4 of the data is less. Okay, so earlier we talked about the median. The median is the halfway point where half of your data is less. The third quartile just kind of extends that a little bit further, and instead of the spot where half of your data is less, you've got 3/4 of the data is less. Okay, so rather than saying this is the spot where half of the data is smaller and half is bigger, here this is the spot where 3/4 of the data is smaller. Okay, so with that in mind, what do you think Q1 is? Yeah, the first quartile, it's the spot where 1/4 of the data is less. Okay? All right, and so the way we find the quartiles is we take our list of data, we arrange them from least to greatest, and then we find the median, okay? That's this halfway point. And once we find the median, we've essentially split our list into a smaller half and a larger half, okay? And then all we do is we just take the smaller half and we find the median of these numbers, and that's going to be our first quartile. And then we take the larger half and we find the median, or the halfway point, of these datas, and that's going to be our third quartile. So it's just the process of taking the median, but you do it 3 different times. First with the whole data set, then with the smaller half, then with the larger half, and that's going to give you Q1, the median, and Q3, or your third quartile. Okay, so to find the quartiles, first find the median, okay, which effectively splits your list in half. Okay, then take each half and find the quote median of those, each of those halves. Then take each half find the respective quote medians of those halves. Okay, so let's I'll give you guys a minute to write that down, and we'll try this out with a set of data. Okay, a small set of data. Let me just make up some numbers, and we'll find the median, we'll find Q3, Q1, the range, the IQR, we'll do all of this fun stuff here, okay? I'm gonna flip to the next slide, if that's all right. All right, so let's imagine I have, we have test scores of, let's say, 16 students, okay? And I'm just gonna make these up, okay? And I'm going to put these in from least to greatest already. Now, sometimes you're going to have to arrange these from least to greatest yourself. But, okay, so let's say our lowest score was 54. Then we had a 60, and a 64, and a 70, another 70, a 72, a 76. 1, 2, 3, 4, a 78, an 81, an 82, an 85, an 88, a 90, a 92, a 94, and a 98. Okay? I think this is 16 scores. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Good. Okay, so we have 16 scores. Okay, so let's find the median. So the median is the spot where how many are greater and how many are less? 8 are greater and 8 are less, right? Okay, so 8 greater, 8 less. Okay, so these are already arranged from least to greatest, so I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to draw a line right there, and then this will also give me 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I have to just find the spot in between 78 and 81. Okay, so I do 78 plus 81 divided by 2, and this will be my median, which is 79.5. So my median is equal to 79.5. Is that okay with everybody? Okay, great. All right, so now let's find the first quartile. Okay, so I found the median, which splits my list into 2, and basically now I have 8 numbers that are less on this side, and I'm going to find the median of these 8 numbers. Okay, and where is that going to be? Okay, I'm going to draw a red line here. I've got 8 numbers, so I want the spot where 4 are more and 4 are less. Okay, so this is going to be Q1. So what is my value for Q1? It's in between 70 and 70, or just plain old 70, right? So that's simple enough. Okay, what about Q3? Okay, I've got 8 numbers up over here. So the halfway spot is going to be what? Between 88 and 90. So what is that? 89, right? I could add those two together. I could do 88 plus 90 over 2, or you might just recognize that that's going to be 89. So Q3 is 89. Okay, and so let's ask, what is my range of scores and what is my IQR? The range is the largest minus the smallest, right? Or my max minus the min. So this would be 98 minus 54. I have a range of 44 points. My IQR, this is Q3 minus Q1. 89 minus 70, I have an IQR of 19 points. Okay? And so don't forget, you know, what do the range and IQR tell us? They are numeric summaries for spread. Okay? So the standard deviation is one way to summarize spread. The IQR and range, they're also another way to summarize spread. Okay? And so, you know, we can use these to compare data sets to data sets by looking from spread to spread. And so we can say, oh, you know, this test class had test scores with a range of 44 and an IQ of 19. Maybe someone else's class has test scores and the range is 30 and the IQR is 10. What does that mean? That means the other class had a smaller spread in scores. So maybe they were more concentrated around certain values or something like that. Okay? I didn't get to cover the concept of box plots, but look in your textbook. I think it's rather straightforward. It's just a way to graphically show kind of 5 key values: Q1, Q3, and the median, plus the minimum and the maximum, and they make an appearance in the box plot. It's just another way to just graphically display these numeric summaries. Okay. With that, I'll let you guys go. Be sure to look at the practice quiz that's posted, and we'll see you guys next week.